The last topic we're going to cover in this chapter is complex zeros. So let f of x be a polynomial whose coefficients are real numbers. If r equals a plus bi is 0 for f, then the absolute conjugate is also a 0 for f. And we've seen complex zeros before when working with quadratics. For example, we've seen this before when we would use the quadratic equation for quadratic functions like f of x equals x squared minus 2x plus 2. Now there are no factors of AC, which in this case is 2, that add up to b, which is negative 2. That tells me I have to use the quadratic formula. So here I have x equals negative b, which in this case is negative 2, plus or minus the square root of b squared minus 4 times a times c all over 2a, which is 1. So I'd get x is 2 plus or minus the square root of negative 4, because it's 4 minus a positive 8, negative 4 over 2. So I get x equals 2 plus or minus 2i over 2. So x equals 1 plus or minus I. So that means x equals 1 plus I and x equals 1 minus I. And these are conjugates. So here's some more examples of complex conjugates. If I have 3 plus 2i, its complex conjugate is 3 minus 2i. If I have 4i and negative 4i, I also could have negative 5 plus I and negative 5 minus I. And the reason we want complex conjugates is because if we were to multiply x minus 1 plus I and x minus 1 minus I, right, those are our zeros. If we were to FOIL this out, we'll get back to f of x, this original function I defined. So the complex parts cancel out. So let's list all zeros of the following. So a polynomial of degree 5 whose coefficients are real numbers has the zeros negative 2, negative 3i, 2i, and 4i. I want to find the remaining two zeros. Well, I need the conjugate of a negative 3i, which is a positive 3i, and I need the conjugate of 2 plus 4i, which is 2 minus 4i. Now, what if I have a polynomial that's degree 3, meaning its zeros are 4, and I'm given the zeros 4 and 3 plus I would also have the 0, 3 minus I. I have to include that conjugate. So how do I find the complex zeros of a function? So the degree of the polynomial is the possible number of zeros. It could have that many zeros or less. I need to first find the rational zeros, right, using the methods we've talked about earlier in this chapter. And then I can factor the quadratic that remains using the quadratic formula. So let's find the complex zeros. For this one, we're going to use use substitution. Think way back to I think we did this in chapter 8, when if I had something that was quadratic in form, I could rewrite that using use substitution. Because if I have f of x equals x squared squared plus 5 times x squared plus 4, I could let u equal x squared and solve this equation. So I have 0 is u squared, because I'm substituting in, it's use substitution, plus 5u plus 4, and I want to factor this, and I say, what are the factors of AC, which is 1 times 4, so 4, that add up to b, which is 5. Well, how about 1 and 4? So now I can factor this, because my leading coefficient is 1, as u plus 1 times u plus 4. Now I can substitute back in. I've got 0 equals x squared plus 1 and x squared plus 4. So I have x squared plus 1 is 0 and x squared plus 4 is 0. I think you might be able to see what's going to happen here. I have to subtract 1 from both sides. So I get x squared is -1. We take the square root of both sides. X equals plus or minus I, because when I take the square root, I have to take plus or minus, which gives us our conjugates, right? If I subtract 4 from both sides, I get x squared is 4. Sorry, a -4. Square root of both sides, x is plus or minus 2i, because the square root of 4 is 2, but it's negative, so it's 2i. So here are my 4 zeros of this degree 4 polynomial. It's important to note that it only has complex zeros, right? So if I have complex zeros, that means that my graph doesn't touch the x-axis. So why don't we graph this in Desmos and see what it looks like? So here's a graph of our function. As you can see, it has no x-intercepts, which is why it has complex zeros.